So, what we have going on today is we're going to be talking about forces, which specifically talking about Newton's second law and free body diagrams. So, what is Newton's second law? Put simply, Newton's second law is that the force on an object equals the mass of the object multiplied by the acceleration that that object will experience. Okay? If we get into a little bit more specific, the force vector, okay, of the net force means the amount of unbalanced force on an object, equals the mass of an object times the acceleration vector. Basically, if you apply a small force onto a body, you're going to get a small acceleration. Okay? Where if you increase the force that you apply on a body, you are also going to increase the acceleration. Looking at it from another perspective, okay, if we have a bigger object, one with more mass, we're going to need more force in order to get the same acceleration. So sometimes you'll see it written like this, force equals mass times acceleration. Another common way that you'll see it represented is that the acceleration equals the net force on an object divided by the mass. Okay? The units for this, our acceleration is in units of meters per second squared. Our net force is in units of newtons, which we abbreviate with a capital N. A newton is actually a shorthand for a kilogram meter per second squared. We just didn't like writing that over and over, so we changed it to the newton. And by we, I mean scientists who came long before me. And the mass is in kilograms, okay? Because our newtons are in kilograms, we always have to make sure that our mass is also in kilograms. So, let's look at some of the forces that might be acting on our object. Okay? One of the forces that acts on a lot of objects, like this pen I have right here, it fell down because of gravity. Okay? Gravity is a downward force. And there is actually an equation to find the force of gravity. We have a different name for force of gravity in our everyday life. Okay? Force of gravity is the exact same thing as the weight of an object. Okay? That is the more common word. We typically think of weight and mass as the same thing, but in physics class, it is not. Okay? The force of gravity, which we define as the weight, is the mass of that object, again in kilograms, times g, our acceleration due to gravity. G is equal to 9.8 meters per second squared, and it's always downward, so sometimes we'll use that as negative, but as long as you know that gravity goes down, you're good to go. Okay? Now, imagine we have a table. Okay? I'm going to draw a super great table here. Okay? And I have an object sitting on the table. Say it's your physics book. The force of gravity is going to pull down on the object, but it's not going to accelerate downward, okay? It's not going to go crashing through the table to the floor down to the center of the earth, because the table is exerting a force back up on that object. It's normally there, so we call it the normal force. Anytime an object is on a surface, the normal force is counteracting the force of gravity and making it just sit there and not randomly go floating up or go crashing down. Okay? And I typically use F with a little n on it for normal. Applied forces are the things you typically think of as forces. They're when you push something, when you pull something, when two objects crash into each other. Okay? That's an applied force. Okay? One of the other forces you might be familiar with is the force of friction. Okay? So friction only acts on objects on a surface. Okay? If it's in the air, we call it air resistance, and that we'll talk about next. Okay? So friction never acts and like helps something go faster. It always stops motion. Okay? Friction is the force that causes a book to stop when you slide it across the table. even though that's counteractive to Newton's first law, an object in motion stays in motion. Friction is that unbalanced force that acts on it that makes it stop. So friction opposes motion on a surface. Okay. Another common one that we'll talk about is air resistance. Okay. Air resistance is super important for people like skydivers who use their parachute to increase their air resistance. It's the force exerted by the actual molecules of air running in to that parachute or that person. Okay. And then we have tension. Tension is the force whenever we have something like a string or a cable holding someone up. In that string or cable, there is tension. Okay. This is important for people who design things like elevators and stuff like that, or need ropes to do a lot of their work. They need to figure out what tension force that string can handle before it snaps. And I realized I forgot to include something about friction. Friction also has an equation. It is that the force of friction equals mu, which we call the coefficient of friction, multiplied by the normal force. The coefficient of friction is basically, hey, how much friction is there? Things like sandpaper have a very high coefficient of friction, where things like ice, okay, has a very low coefficient of friction. And then the normal force is there because friction also depends on how heavy the object is. The heavier an object is, the tighter it sits down on that surface, the more friction there's going to be. Okay? So again, that's mu, which we call the coefficient of friction. And this one is the normal force, okay? The force that opposes gravity along a surface. So that's the definition of all these forces. And all of these are important when drawing our free body diagrams. So, how we use all of these is to determine how these forces interact with each other. The forces are balanced. So I'm going to go ahead and erase these notes real quick. And we're going to look at a tug-of-war situation. Okay, so if some kids are playing tug-of-war, and this group is applying a force of 300 newtons to the right, and this group is applying a force of 300 newtons to the left, the forces are balanced. Okay, and the amount of unbalanced force, or the amount of leftover force, we call the net force. And the net force, or unbalanced force, is what causes acceleration. So in the first situation where the forces are balanced, 300 newtons in each direction, there's no net force, force net, which means there's going to be no acceleration. That rope isn't going to move. Where in the second situation, where we have 400 newtons to the left and 300 newtons to the right, our net force is going to be 100 newtons to the left. That's the amount of unbalanced force, which means that there's going to be a leftward acceleration. Okay? The direction of the net force, or of the unbalanced force, is what determines the direction of the acceleration, and along with the mass determines how much acceleration there will be. Okay? So net forces cause acceleration, net forces cause acceleration, net forces cause acceleration. None of these forces on their own can be used to determine the acceleration, unless it is the only force acting on that system, which isn't that likely. Okay? So let's look at some example problems. Example number 1. A rabbit pushes a 0.5 kilogram carrot towards its burrow. The coefficient of friction between the carrot and the grass is 0.45. If the carrot accelerates at a rate of 2.0 meters per second squared, what force must the rabbit be applying? Okay, so with any of these problems, the first thing we're going to do is draw our free body diagram. So here's my object. It's a carrot. I don't want to draw a carrot, so I'm just going to draw a box. And it is 0.5 kilograms. Okay. And it's pushing it towards its burrow. We'll say that its burrow is over there. Why not? So it is applying a force. Okay. It says that there's friction between the carrot and the grass. So we know that there is some force of friction. And it is accelerating. Okay. So the acceleration is 2.0 meters per second squared. Okay. And then we know that the coefficient of friction, mu, is 0.45. Okay, let's talk about some other forces acting on this carrot. What force is keeping the carrot down on the ground? Gravity. And what force is keeping the carrot up on the ground? I guess you could say the normal force. Okay. And right now, the only force that's causing the acceleration is some unbalanced or net force in this direction. So let's do some math and figure out some things. So right now, I can use my acceleration to find my net force because the net force is going to be what's causing the acceleration. So my equation is net force equals mass times acceleration. My mass is 0.5 kilograms. My acceleration is 2.0 meters per second squared. I plug that into my calculator. And I get 1. Yes, I had to plug that into my calculator. Don't judge me. So 1.0 kilogram meter per second squared, aka newtons. So I'm going to add that to my picture over here. Force net is 1.0 newtons. That means that's the amount of my unbalanced force. Okay? Now I know my coefficient of friction, but I don't know my force of friction. However, I do know that the force of friction equals mu times the normal force. This is an equation you'll typically be given on an equation sheet. But guess what? I don't know the normal force right now, but I can find it. Okay? Because I know the object's mass, I can find the force of gravity or the weight of that object. So the force of gravity equals mass times g, the acceleration due to gravity. So 0.5 times 9.8, and I get 4.9. So the force of gravity acting on that carrot is 4.9 newtons down. That is balanced out by the normal force going up. So the normal force also equals 4.9 newtons, just in the opposite direction. Okay, they're all the same thing. So to find my force of friction, change to another color for you guys. Force of friction equals mu, which was given to me in the problem. It was 0.45, times the normal force, which we just found to be 4.9. We plug that into our calculator, and we get 2.2 newtons. Okay. So I'm going to fill that in on my free body diagram. So now we just need to find what force the rabbit is applying. What is this applied force by the rabbit pushing on that carrot? Well, the force of friction is opposing that force. And the net force, the total unbalanced force that's causing that acceleration, is 1.0 newtons. So the applied force is going to equal the net force plus the amount of friction, okay? Because that's the stronger force, so it has to be more than what it was before. So when I do 1.0 plus 2.2, I get 3.2 newtons. So the rabbit must be applying 3.2 newtons of force. Sorry, it looks like 0.32. Let me fix it. In order, we can always check it. Okay, if I have 3.2 newtons to the right and 2.2 newtons to the left, that does give me a net force of 1.0 newtons to the right. And we know the rabbit is succeeding in pushing it towards its burrow. We used our acceleration. We used all the pieces. We used every single equation that we knew for forces. And we got our answer. Okay? So again, on these types of problems, don't try to look for one easy step by step. Every problem is different, and you just have to analyze what you're given. Okay? So let's look at another example that might be a little bit different. A weightlifter is attempting to lift a 50-kilogram block. What force must he apply in order to cause the block to accelerate at 0.5 meters per second squared? Okay, so we have a block, a weight, okay? It is on the ground, and it is attempting to be lifted. In order for something to lift, even to go to a slow velocity, it has to accelerate from 0, where it was, to what it's at now. So there is my block. It has a mass of 50 kilograms, okay? And we want it to accelerate at 0.5 meters per second squared. Something tempting to do here would to be like, oh, that's easy. The force equals mass times acceleration. The mass is 50 kilograms. The acceleration that we want is 0.5 meters per second squared. We get 25 newtons. And to stop right there. Okay? That is a number that we do need to know, but it is not our answer. Because if you look at the free body diagram, okay, the weightlifter does have to apply a force and lift it up, but he's not lifting it up in a vacuum. Okay? There is a force that is keeping that block down on the ground. What force is that, you might ask? Well, it is gravity. Okay? Gravity is keeping that block down on the ground. While it's resting at the surface, the table is doing the normal force and causing it to stay there. But that second he tries to accelerate it off the ground and it loses contact with that, guess what? The floor ain't going to help keep it there anymore. Okay? So he's going to have to overcome the force of gravity. What we found here is just the net force. Okay? So that is the net force that we need. Undo. Okay, so that is the net force that we need. I can go ahead and add that to my free body diagram. That is the force needed to cause that acceleration. But we need to figure out how much force he has to lift it, because he's going to have to lift it a lot more to overcome the gravity going down on it. So we remember force of gravity equals mass times the acceleration due to gravity. So that is going to be 50 kilograms times 9.8 meters per second squared, which gives us a force of gravity, plug it into your calculator, of 490 newtons. So there are 490 newtons pulling this block down. We need a net force of 25 newtons. Okay, so we need the applied force, we need the applied force to be greater than the force of gravity by 25 newtons. So the applied force is going to equal 490 plus 25, which gives you 515 newtons. So that's how much force, upward force, has to be applied in order to actually lift that block. Okay? And again, the block's not moving side to side at all. It didn't say anything about that. So we don't have any of those forces going on. Hopefully that was helpful. Do you get it? Okay, cool? Okay, cool.